Hello, grade eights. Welcome to your second lesson of Unit 7, third last lesson of the year. We're going to be talking about misrepresenting data on graphs today. So basically, how do you make a graph that says what you want it to say, not what it actually says? Or how do you make a graph that, companies might want you to see that promotes their company better when it's not actually the truth? Or in politics, how do you make it look like you're actually winning if you're not? How do you make it look like something you've done is favorable when it's not? That's what this is all about. So how do you, outside viewers, you people who are looking at the graph, or how can we make it so that you're able to see a graph and think, that's not quite what it's trying to do. I see through what you're trying to do. Okay, that's the game plan. So what I'm going to do is use these two links that I'm clicking up here. They are perfect. I thought about going with my own lesson. I liked these better this time. So here's what we're going to go with. This one is vengage.com, and it's 5 ways that writers use misleading graphs. So we're going to just discuss these here. I'm going to give you my input on these. So the 5 ways. Number 1, omitting the baseline. So what omitting the baseline is, notice the data on the y-axis here and the data on the y-axis here. In this one, they started at 50. In this one, they started at 0. 0 is accurate because in this one here, you see what it does to the bars. Look at the bars in this one. Look at the bars in this one. When you start at 50, it over-represents Group A. It makes Group A look like they're doing a great job. And in truth, it's a lot closer with Group B and C. But if you adjust the data that's on the side of the graph, it can really mess with things. So omitting the baseline, not making it start at 0, totally torches the way a graph looks. Avoid it. If you see it, know that's probably the problem. 2 is manipulating the y-axis. You are the one, when you make a graph, that gets to decide what kind of a scale you put on the y-axis. But if you make that scale either too big or too small, you change the way things look. This is showing you all the same bottom part, 2019, 2023, but this one goes 0, 10, 20. It's counting by 10s. And this one goes 0, 5, 10, 15. It's counting by 5s. Look at the difference in the line that's on the graph when you go up by 5s and go up by 10s. This graph here is trying to make it seem like there's not that much difference between the years that are there. This graph is actually showing you that, yeah, there is a dramatic difference here, but it's all about picking the right scale. I could make this say 0, 100, and the whole line would look like it's right here. But that doesn't help us look at the graph. Manipulating the y-axis doesn't work. Torches what you're trying to say. 3 is cherry-picking data. Cherry-picking data means settling on a part on the x-axis that's way smaller and shows what people want you to see. For example, with this one, look at this. May 20th to August 20th. It's showing you 3 months where it's going up. Oh, good. 2019 to 2023 goes up a bit, and then it comes crashing down. So imagine that you were part of a company and you wanted to show a snapshot of your sales. Hey, look, my company's doing great. Look at that. It's going way up, but in truth, you had a little bit of spike in sales and then it plummeted. But if you're trying to get people to invest in your company, you don't want them to see the plummet because then it doesn't look so good. So just realize this is misleading. Okay, they're cheating the viewer of the graph into thinking that things are all happy and good, sales are going up, when in truth, if you look at a bigger picture, it doesn't look so good. The next one says using the wrong graph. Here we have a pie chart. Here we have a bar graph. Now, I kind of don't like this one that much because there's percentages on the bar graph, but the bar graph here is a better idea. And the big reason is that pie graphs have to add up to 100%. This does not. 64 plus 50 plus 38, misleading. That's not 100%, which totally misrepresents the data that's supposed to be there. This is the accurate data. This shows where these things are actually supposed to be. The final one is going against conventions. When people get used to looking at graphs regularly, they start to see patterns, okay? This one's talking about population density. So in other words, how many people are in certain areas that are busy versus how many areas that are in certain areas that are not busy. But when you see graphs like that, people are used to seeing these things so that 60, the black color, is usually indicative of more people. So if you look at this one, yeah, it's showing you that there are some areas where there's more people. Shouldn't shock anybody. lots of the places in the eastern United States, whatever, less in Alaska. But when you do it here, they've switched it so that the part that's white makes it look like there's less people there. But really, that's where there's more people. So going with what's normal and making a tiny little switch can make everything change in terms of what your perception of the graph is. So that's the fifth one, is just changing the way things are normally seen. Now, I'm going to flip to this one because this one here shows some perfect examples of each of them, and then we'll call this a video and that'll be it. So here they are. Number one, what makes this bar graph right here difficult to read? What makes it look wrong? Well, if you look at the bar graph, and I'm actually going to zoom this in a little bit, notice that on the side, it makes it look like house prices went way up. Holy smokes, between 98 and 99. House prices go way up. Well, the truth is that they didn't go that high up because if you look down the side, they didn't start this at zero. This would be 79,000 here. So the house prices only went up by like $2,000, but it makes it look dramatic, like it went up by a ton. If this started at zero, these things would be around the same level. Okay, so they're trying to, if I had to guess, this would probably be a real estate agent or somebody in the city who's saying, hey, look, now's the time to sell your house because look at how much more money you'll get. You won't get that much more money. It's just misrepresented. There's a better look at it. Hey, that's fair. There's zero now. Yeah, it totally went up by a lot. The next one says, what's wrong with this information? Well, let's take a look. The vertical scale starting at zero, that's fine, but it doesn't go up in even steps. Look at the numbers. By now, you should know that on graphs, look at the horizontal scale. 0, 1, 2, 3. It's going up by 1. The ones up here going up by 10,000, another 10,000, another 10,000, another 10,000. But this one, they're trying to mess with you. 0 to 1, 1 to 2. Okay, we're going up by 1. Nope, we're going up by 2, 4, 6, or 2, 4, 8. That doesn't work. That one's an exponential scale. Doesn't say what it's trying to say. It's misrepresenting the data. This one here, they're saying that 3D charts can be misleading. By putting this in the foreground, it makes it look like it's a lot higher than the ones in the background. But if you look at these like this normally, 95 and 97 are actually the same. You wouldn't be able to tell that from this graph. So doing 3D can be misleading. Another one's talking about deceptive pictographs, and we're going to get to another example of that in a minute. You know how I feel about pictographs from the last video. All right, here is our mess of a pictograph. It's 50 people is this, 50 people's the cat, 50 people's the horse, 50 people's the fish, the dog, I guess that is. Dog, okay. The problem is that the horses are way bigger. The cats are all crunched together and small. So the person who made this, some people would look at this and say, well, the furthest one over here is the horse, so that must be the most. No, it's just bigger, okay? We want these things to all be the same size, so it's fair. Look at this one. Now the cat goes to the end. Fair. Pictographs all have to be the same size. It's about counting how many is for each of them. The next one here is showing a pie chart. Again, this is just like our situation from before. The percents don't equal to 100, so it doesn't quite work. We need to make sure they equal to 100. Here's the last one. This one's talking about data. And again, it's kind of changing the way that the graph looks. This one here, first off, they're doing this thing, which means it's not starting at 0. Again here. But this one's really going up by 50, 50, 50. This one's going up by 10, 10, 10. So depending on the data you use, it shows either way dramatic or it's flattening the line and making it seem. They're not conveying the same message. The space in the years is more spread out. If you do decide to go back to this site, there are practice problems that you can look at yourself. So I'm going to leave that as an option for you. Let's look at some of the ones in the textbook, and then this will be the end here. Here are some graphs. By now, if I gave you 5 seconds to look at this, you should be able to kind of see why they're different. And here it is. This one starts at 0. This one, didn't start at 0. It makes the differences look a lot more dramatic than they actually are. So again, this one's about house prices. Wow, look at how much house prices are going down. You should definitely buy in this city, is what the real estate agent is probably trying to convince you. They haven't gone down that much. They've gone down a little bit. You're not going to make a big difference, but it's all about how you represent the data. This one right here is a useless graph for many reasons. Number one, it has no numbers. You can't tell. It says annual precipitation. Great. If there are no numbers, you have no idea what it means. Now we have numbers. Cool. So this is a perfect graph, right? No. This one starts at 250. Whitehorse looks like it has no rain. But if we start at 250, yeah, that it does have some rain. It's just trying to make it look smaller, I guess. There's the one that we want, starting at 0 all the way up to the top. Lists everything. You can compare them accurately. Data not misrepresented. Here's a dumb one. Grade 8 students scored higher on a math test, girls or boys? I would say it's probably a boy who wrote this thing, because the boy doubled the size of the boy's line or bar to make it look like it's so important, when in truth, the girls win this round, guys. Sorry, but the girls win. It's a little higher. Boys are lower. In this case, boys probably cheated and widened their bar so it looked more important. Got to keep the bars the same. Here's our pictograph example. Everything needs to be the same size in order for it to be fair. Here is another one, but with scaling. Here the scale is really big, going up by 10 each time. Here the scale is up by 3 each time. This is the accurate one because you can see very easily the differences when you have a smaller scale. The biggest number is 11. So why is anything up to 50, anything past 20 should not be on this graph? Because there's no data there. So we need a smaller scale. Here's another little sneaky one that they do with circle graphs. Notice what they've done with this milk. They're making it look like milk is the biggest one because they've pulled it out. They've grabbed it and taken it away so it draws your attention. When in truth, water is actually the biggest one, but it's how you represent it. Here are some other ones. I'll leave you with these examples. I've talked about this enough. You can probably see that this one's not at 0. Should be at 0. Look at the difference in the line. When it's not at 0, bow, dramatic. At 0, flat. Others here, you're welcome to take a look at them. The stuff will be assigned soon. And thanks for watching the video. We'll see you next time.